As a disclaimer, I would like to start with that we did these studies as application scientists, and it doesn't mean that the team is not constantly checking the speed when they are developing the tool. So this is not the one that's in their build pipeline when they are committing any lines of code and they are testing the performance. This is about exploring the capabilities, and this is about trying to independently look at the tool, not being within the developer team. And we are running these tests regularly. That was the third etap of such tests. I will talk about JChem Oracle cartridge performance, PostgreSQL cartridge, and Coral. And I use this designation that's next generation, since these are the latest two are utilizing the new technology, the new engine. One is interfaced with Postgre, the other is with Oracle, as it was introduced by András Wolford. Just some words about the setup itself. We selected 49 custom selected structures as being the queries, mostly for substructure search, but these are useful queries as well for similarity search. Some of them are from the JMedChem, the rings of drugs. What you can see, so the most frequently occurring drugs, the rings in drugs or ring systems, as well as some exact molecules, drugs, or queries which are not that selective. And as András mentioned, benzene is not the best query, and you will never ever run a query with that. That's not here, that's not listed here, but we have a couple of other tricky queries as well. In total, with these 11 queries, including query features, we ended up with 60 different query molecules. And started to run our tests first on MQL database, which is 42 million structures. This was imported or inserted into a single table, so there is no relational data. It's just one table with the structures and the corresponding IDs. And we measured substructure search performance, substructure search with limit 100, and I will use this when we are looking for the top 100. And in this new technology, this top 100 will not be random. These will be those substructure hit queries, those substructure hits that are most similar to that of the query. And also we run similarity search as well as similarity with top 100. On this graph, what you see, and I will use this graph later on as well, you see the sum elapsed time ratio compared to JChem Oracle cartridge. So we run the 60 queries, measured what was the total elapsed time, and divided the JOC total time with that of the JPC or the Coral. The JPC will be this bluish color, the Coral will be gold in all of my slides. What you see here is that you can see 15, 16 times speed improvement for substructure search limited queries, 20 or 30 times faster speed with similarity or similarity limited hits. However, the substructure search doesn't seem to really perform better. And we started to investigate this and plotted the hit count in terms of in function of the hit count, the elapsed time for Coral, JPC, and the JOC. And what you can see on this graph is that what was the speed that, or what was the elapsed time needed for a given query to run and give back the results. These are the well-known standard Oracle cartridge, and as you can see, these are the performances with the two new techniques. What you can discover is that when the hit count is low, and under low I mean 10,000, the speed improvement is quite univocal, we can say. However, in this range, it's more scattered. So if you would like to get back hundreds of thousands or millions of hits, then you want to experience this speed up. And that indicates how you can use and utilize these performances. If you are thinking of a drug discovery use case where you have combined queries, you might not get, or you might not want to visualize hundreds of thousands of structures, since that's not that meaningful. In that region, you might utilize offline queries, and speed is not that important factor in your workflow. When we divided these two, so we divided the speed of the Oracle cartridge with the PostgreSQL or the Coral. So this is the ratio, as you could see. So this region will have high ratio and the other one will be low. So this is about 7 times faster, and this is close to 1, and some which results in 1 million hits. That's just lower than 1. So in this case, the speed is decreased due to some reasons. And the median of these ratios is about 2. So you can expect that 50% of the cases, if you have these diverse substructure queries, will still get 2 times faster with the new technologies. So in summary, we see significant performance improvement on limited substructure or similarity screens and searches, and that's also true for the substructure if you have a low number of hits, so lower than tens of thousands. Then we also tested this on Campbell database, which includes 1.8 million structures, 50 million activities, and here the whole Campbell was imported into the database. And we also applied a combined query where we defined a target that it should have activity in the activity table, it should have a given substructure, but it shouldn't have another one. So we had in total 4 elements in our query, and we joined these 4 tables and run these combined queries as well. Here you can see the results from Campbell. As you see, this is the substructure limit. Again, we see some improvement, similarity not as big as with the larger set. The limited similarity, again, we could achieve more than 10 times faster speed. And in complex queries, the Coral resulted in 3 times faster results, while the new Postgre cartridge yielded 13 times faster than the previous one. And we discussed the substructure results as well. These were measured on EC2 instances with Oracle Enterprise license and with Oracle Enterprise system, and these results were generated last November. And before the UGM, we said that we would like to investigate more and just go into some details, bits and pieces of this system. And in the first case with MQ, it was a simple table, so it was just substructure search. Might not resemble a real-life use case, or not all of the use cases. Campbell was more like a real-life use case, what's being done in the drug discovery settings. You have multiple tables and you have to join them. However, we try to avoid caching of the query plans or any trick that Oracle or Postgre can do, and therefore we had different queries for every and each, and that resulted in a difficult situation since we didn't know what to expect from Campbell. How many hits do we have at the end of the day? So whether the additional condition will be too selective or not. We didn't have measures in front, and therefore, it had some variance what we couldn't predict before we run all the queries, and therefore decided to have a more laboratory-like test case, but still with the relational data. So we imported 10 million structures from MQ and added 30 million numeric values to mimic measured biological activities, which is a one-to-many relationship. For every and each ID, we generated 3 numbers, and then started some investigations on this. But at this point, the team discovered something peculiar thing in Oracle is that Oracle insists on planning. So even if you have a straight road like this, I don't know if this was shot in California or not, but something very straight, you only have a substructure query. Still, Oracle is asking for a plan for a cost from our cartridge, and this cost estimation takes for a while. And this is this time that takes for the cost estimation is significant part of the very fast queries. So therefore, the team suggested that somehow we should trick Oracle and skip this planning. And they had this idea that we should add a dummy function called avoid planning that just returns the very same number as a varchar. And if we use this within our query, then Oracle won't be able to do this planning. And it had quite nice effects. Now I'm showing you substructure search limited query results on this 10 million set with this no planning. Here you can see the time. This is the number of, or the percentage of queries not finished. So 90% of the queries were finished in 1 sec. With JPC, some 2 seconds or less than 2 seconds with Coral, and that took 200 or 100-ish seconds with the Oracle cartridge. So we also measured this no plan with Oracle cartridge as well. So here you can see a very nice speed up. So if you are looking for this really interactive query, you only have substructure queries, and you introduce this no planning, you will achieve quite nice speed improvements. If we show the results in terms of the elapsed time that JOC needs to run the queries, you can see the JOC with no plan. It's not that big effect. Here you can see the Coral with planning and the empty triangles without planning. And these dots, the full dots are the JPC, and the empty circles are the JPC without planning. So this is really affects Oracle, not Postgres, since Postgres is not doing this unnecessary cost estimation call towards our engine. But Oracle does this, and if you compare these dots to those ones, you can see that there is a impressive difference. And these lines are just symbolizing, this is a log-log plot, that this is a 1-to-1 ratio, 10-to-1, 100. So this line is when we have 100 times speed up. Every point that's below this line is more than 100. This is 1,000 times speed up. So we can even achieve, in some cases, 1,000 times speed up with the queries. So what does it mean? If we just run this substructure limited search, it's about 8 or close to 100 speed up in this 10 million set with Coral and Postgres respectively. However, when we introduce this no plan, it will be 50 times and close to 80 times speed up with the JPC. So as you can see, we do have speed up. So that's to back up what was said by András Wolford. But our goal was to, with this test case, to have control over selectivity in this additional data table. And we wanted to utilize this control in a setup that we have a non-selective data query or a selective data query plus the chemical. We assume that if the data query is non-selective, then the chemistry will be run in index mode, in access mode. However, if the data is selective, then the chemistry will be executed in a filter mode. For those who are familiar with terms of RDBMS systems, so these are 2 ways how the data can be fetched. Basically, access is using the index, so it can effectively search in the tree and get back the results fast. While in case of filter, it's asking one by one our service, since it used the other index, it used the index on data. And we got these results when in this setup we tried to push towards the access, the index mode. It was 1 and 1.3 times faster than the Oracle cartridge. However, in filter mode, it was 2.5 or 7 times faster. We went with the filter mode and wanted to see from the query plans whether it's really doing what we designed. And it turned out that the Oracle cartridge is still, in 90% of the cases, uses the access, not the filter. while in case of Coral, it was 50-50, and JPC behaved as we want it to behave. In 87% of the cases, it really did the filtering. And that's important to be noticed here or emphasized here, that we expect a higher speed up with filter. And that can reason why the JPC had higher speed up compared to the Coral, where almost half of the cases went into excess mode. And the JOC did not behave that well as we wanted. Here again, the very same chart. This is the time, query is not finished, and you can see how much time do you have to wait until a given percentage of the queries are finished. And here you can compare how much the JPC or the Coral is faster compared to JOC. And this is again in terms of the JOC elapsed time. What you can see in this filter mode is that the JPC is really 10 times faster in most of the cases, and the Coral is in between 1 and 10. The other case was this excess, where we didn't have that much speed up, and we wanted to understand why. And this excess mode will resemble the very same as we had a table with only chemical structure, since it will use the index first, and it will not go into functional mode, filter mode in the query. So if it is plotted in terms of the JOC elapsed time, the Coral or the JPC in excess mode, you can see that the fast queries were even faster, while the long queries didn't show remarkable speed up. But this chart really close to the one what I showed before with only substructure queries, since what we have here is that since the additional condition is not that selective, it's just doing the very same substructure search. At the end of the day, we have less hits, since then the two will be combined. But what you see here is, again, if you have low number of hits, then there is a significant speed up, while in those cases when we got back hundreds of thousands, this will vanish and you won't have the speed up. So that was all. Sorry, I tried to keep the time, and she asked me to, so I tried to speak fast, but I hope that was clear, all the charts for you. If you have any questions, you can ask Ju, András, or myself. I did the data analysis, but they developed the code, so feel free to contact. And my summary is that if performance matters, save time with the next generation engines, Coral or the PostgreSQL cartridge. And with that, my message was that you don't have to save time for evaluating these ones, since you could see the results already, so you can start just using it. Thank you for your attention.
Basically, the Postgres is faster than the Oracle next generation for both of them. The things that were on there, it's faster. Is that because you guys have been working on Postgres for a couple of years and Coral's really new, or is it more like related to the architecture or what Oracle is doing versus Postgres?
It has several reasons. One of them is the architecture, so we are working on that as well, because we are using another kind of connection between the Oracle and between the service as in Postgres. So that is one of the reasons. But we can, because we were aiming for Amazon RDS, but since last October, Java is already available in Amazon RDS, so that's why we can now switch to a much faster connection type than HTTP, and this will have better performance in combined queries. This is one of the reasons. Another is that in those cases that Ákos measured, Oracle's cost estimation, Oracle's statistic gathering didn't work that well as Postgres is. So Postgres performed there better. And that's why it went to filter mode most of the times. And yes, what else? Yes, and Postgres is parallel in filter mode always, so it is available. But our last measurements with Oracle were on standard edition, which is not parallel in filter mode, but it is in enterprise mode.
Yep, so there is another factor is that these are different databases, so that's really affects. When I had these pie charts, we discussed this deeply with Ju, that this is due to the different sampling and statistics in Oracle and in Postgre. And in this case, Postgre did better job.